Okay, been a while since we've been in here for lecture. So last class we talked about periodic law. We were starting to jump into talking about the periodic table, some of the fun stuff that's on there, some of the cool things about the way that it's arranged. We'll be explaining some of those patterns, those properties today. So that's cool. Previously, the periodic table would have been laid out something like this just long row of things here at the bottom. But thanks to Dmitry Mendeleev, we've got it laid out more like the periodic table that we have today. And they filled it in and probably rearranged it a little bit. And there's still some discussion about how things are rearranged. It's all just based on observations. And I think that this is the slide that we ended on last class. So we were looking at different ways of categorizing things on the periodic table. One big broad strokes way of talking about things on the periodic table is everything on the left and kind of more towards the bottom is metals. Most of the periodic table is things that we would consider metals, things that we would identify as metals. A lot of the things in the middle section, which we'll talk about later, a lot of things in here are things that we would recognize as metals, things like copper, iron, titanium. Aluminum is, I think, this cell. And this is in the semi-metals region. Semi-metals is kind of a fuzzy region. The one that's like real hard and fast that I would recommend that you know is silicon, which would be in this square with the way that it's laid out. I don't know that this is all the cells that should be there, but it doesn't matter. So silicon is one that you should definitely know is a semi-metal or metalloid. And then nonmetals is kind of everything up and to the right, and people also usually include hydrogen in that. So that's the one oddball from the left side of the periodic table. So our metals occupy the left side of the periodic table, most of the periodic table. And they've got similar properties, things that we would identify as properties of metals, the reasons that we use metals for the things we do. They're good conductors of heat and electricity. They can be pounded flat into sheets or drawn into wires. They're often shiny. And important for us, they tend to lose electrons when they undergo chemical changes. So examples include things like iron, Fe, magnesium, Mg, chromium, Cr, and sodium, Na. Again, this tend to lose electrons when they undergo chemical changes is big and important. Our nonmetals occupy the upper right side of the periodic table. Hydrogen is usually included in the nonmetals. So that's the one weird one, the oddball. And these are sometimes solids at room temperature, others are gases. Bromine, if you look at the periodic table that we have in the class, bromine has the blue symbol and filled in, and that means that it's a liquid at room temperature. Nonmetals tend to be poor conductors of heat and electricity. That's why we don't use them for wires. And they, importantly, tend to gain electrons when they undergo chemical changes. Examples include gases like oxygen, nitrogen, chlorine, and solid iodine. And then in between our metals and our nonmetals, we've got things with intermediate properties that can also be kind of weird. Metalloids or semi-metals. These display mixed properties. They're also called semiconductors because of their intermediate electrical conductivity. So one of the interesting things about some of our semiconductors is that you can tune their electrical resistance. So you can change like temperature, for example, and it changes their electrical resistance. And silicon is the one that you should definitely know. Silicon, typically used in electronic devices, it's usually the backboard or the backbone of a lot of our electronics. Okay, so looking at where these things are on the periodic table, let's try to classify these as metal, nonmetal, or metalloid. So find Se on the periodic table. we've got Se up here, and the periodic table that we've got in class has this bolded kind of staircase line. That's just kind of roughly where we split our metals and our nonmetals, and usually our metalloids are found along that line. Your yellow periodic table also has that on it. So what would we call Se? Cool, I heard a couple of different answers. I would consider it a nonmetal. I think that's probably consensus, is that it's a nonmetal. All right, let's find Mg. Mg we find over on the left side of the periodic table, so what are we going to call that? Yeah, we're going to classify that as a metal. It's on the left side of the periodic table. And then we've got Ge. What do we think Ge is? Yeah, Ge is a metalloid or semi-metal. And then what about Ag? Ag. Ag is metal. Ag for silver. Silver, of course, a metal. Questions about any of those? So again, a little bit fuzzy where the metalloids, semi-metals are. That's why I said silicon is the one that you should definitely know. Okay, another way that we can categorize, or a couple other ways that we can categorize our elements, is we've got things that we call main group and things that we call transition. So our main group elements are going to be our far left 2 columns, our far right 6 columns, and then everything else is transition metals or lanthanides and actinides. We kind of just leave out lanthanides and actinides for most of the class. I think those would also fall in the transition metals category. So our transition metals is just everything that's in the middle here. And these have weird properties. Not really weird properties, varied properties. Especially when it comes to ions, which is what makes them so tricky. So our main group elements, again, these are our far left 2 columns, our far right 6 columns, and then transition metals are everything that's in the nice little rectangle in the middle. For our main groups, some of these also have names. So these columns or pillars, or like pillars, we can also call families. We can also call groups. And several of them have names. Not all of them have names, but several of them have names, and some of those are given here. If you look at the periodic tables in our class, most periodic tables will say what group they are on the top, and they often have 2 numbering systems. We'll talk about why that A numbering system is helpful in a bit. So our 2 named groups to start are the alkali metals. The alkali metals are our group 1A or 1. A just means that it's main group. And our alkali metals are very reactive. Increasing reactivity as you go down. Not that that's particularly relevant, but you can look up videos of people throwing these things in water, and the further down you go, the more reactive they get, all the way down to cesium. Francium is actually less reactive than cesium. There's also a lot less francium in the world. So as you move down the group, the reactivity increases. These are our alkali metals, our first column. And we don't include hydrogen in that because hydrogen is a nonmetal. So those are our alkali metals. And then next to that, we've got our alkaline earth metals. They are fairly reactive. They're less reactive than the alkali metals. What's the group number for our alkaline earth metals? 2 or 2A. And how does that compare to our alkali metals? Is it bigger or smaller? Our alkali metals are 1 or 1A. So 2 or 2A is bigger. So it's a bigger number. And is the name longer or shorter? Alkaline earth? Longer than alkali metals, right? So alkali and then alkaline earth. They get longer as you go. That's the way that I remembered them. So they're a longer name than alkali. And these include a bunch of things like beryllium and magnesium and calcium and so on and so forth. And these are less reactive than our alkali metals. And then skipping to the far right side of the periodic table, looking at our halogens. Halogens, like the name for the light bulb type, are fluorine all the way down. So our halogens are very reactive nonmetals. More reactive, I think, as you get to the top, as you move towards fluorine. One little pedantic note, how would we pronounce the one that starts with an I? Probably iodine. That's definitely an acceptable pronunciation. I've heard a good case for why we should pronounce it iodine. So F, fluorine, chlorine, bromine, iodine, iodine, acetine, tennessine. You can pronounce it either way. I just think that that's interesting. Again, these are very reactive nonmetals. There's a fun video by, I think it's the Royal Society of Chemistry, online of reacting cesium with fluorine gas. It's really interesting. It's our most reactive metal, our most reactive nonmetal, and it goes crazy. So that's kind of fun. You can look that up on YouTube's. Moving one to the right from our very reactive halogens, we've got the noble gases. The noble gases are chemically inert. These do not react, which is mostly true, but also not true. You can get them to react, they just really hate it, and so they'll immediately try to go back to whatever they were before they reacted, like vigorously and viciously. So for all intents and purposes, for our purposes, they don't react with anything, which is great news if any of you have done that trick with helium party balloons, where you breathe in the helium and then you talk and then your voice is pitch shifted up. It's mostly fine as long as you don't do it too much, because then you might not have enough oxygen in your blood. But it's fine to do in the short term. The helium, neon, like in neon signs, also non-reactive, which is great news, because if you break them, they're super hot. And if it was a flammable gas, then they would explode. Another fun party trick you can do, but is a little bit more difficult to do than the helium one, is argon. So the reason that helium pitch shifts your voice up is because helium is less dense than air. That's also why it floats. Argon is more dense than air, and so it'll pitch shift your voice down. And since it's a noble gas, it's also chemically inert, and I think it's safe for you to do. I haven't tried it, but you can watch videos of people doing that trick with argon. I imagine that it sounds pretty interesting. Okay, so some of these have names. Some of the groups that these elements belong in have names. Some of them don't. Might not. Maybe they all do. I forget. Anyway, let's figure out which group or family they belong to, and if it's named, write the name. All right, let's hunt down where these elements belong. Li is lithium, and it's way over here on the far left. What's the name for that group?
Alkaline?
Yeah, it's our alkali metals. Alkali metals, aka group 1 or 1A. How about Ar? Ar is all the way on the right side. It's in our noble gas family. our non-reactive group. So this would be group 18, or if we're using that A designation, it's 8A. It's the 8th column in our main group. And then Cl is right next door. What's the name for that group? Yeah, that's our halogens, which is group 17 or 7A. And then Sr is over on the left side of the periodic table. It's in our alkaline earth metals. Which is 2 or 2A. Questions about any of those? Great. Okay, now to ions. So if you change the number of electrons, there are electrons in elements. If you change the number of electrons, as often happens in chemical reactions, metals tend to lose electrons, nonmetals tend to gain electrons. You can lose or gain electrons, and since electrons have a charge, then that will form charged particles called ions. So ions are charged particles. We've got two names for ions. Our positively charged ions are cations. So cations are positively charged. Cats have pos. And our negatively charged ions are called anions, which kind of looks like onions. And I'm guessing that most of us don't like eating a raw onion by itself. You don't just bite into a raw onion and eat it like an apple, because that would be very bad. But I think the pos and cat connection is a little bit stronger. So when we lose or gain electrons, we get a charge. And the charge of the ion is typically shown in the upper right corner of the symbol, and we write the magnitude or the number of the charge first, followed by the sign of the charge. So for example, barium 2+, we write the number first, and then we write the sign, the positive or negative, after that. So Ba2+, and it's superscripted, so it's the small text, but it's raised. Same thing for negatively charged. So phosphorus, for example, forms a 3 negative charge. We write the 3 first and then the negative after that. Will I still understand you if you write the charge, like the plus or minus first? Yes, but I'll be a little bit annoyed. Just because this is the convention, so please use the convention. All right, so some examples of how this might occur. In a reaction, lithium atoms, lithium's a metal. Lithium can go to lose 1 electron. So we get lithium plus, and that electron still exists, it just went somewhere else. And so that forms lithium plus. The charge of our ion depends on how many electrons were gained or lost. If you lose 1 electron, you get a 1+ charge. There's a couple of ways that we can think about ion charge. I'll try to remember to talk about those in a little bit. Generally, though, just our ion charge, it's the number of protons. We can figure out the number of protons by looking at the atomic number in our class periodic table. It's in the top right corner. Sometimes it's in the top and in the middle. Other times maybe top left, but always in the top of the cell. That's the number of protons that we have. Each proton has 1+ charge. And then the number of electrons in a neutral ion or a neutral atom is going to be the same as the number of protons. So for our lithium, we have 3 protons and 2 electrons because we lost 1. And so we have 3 protons minus 2 electrons, overall we've got a 1 positive charge. We can also gain electrons if we're a nonmetal. Nonmetals tend to gain electrons. So for example, fluorine can gain 1 electron. Fluorine plus an electron goes to F minus. If we have a charge of 1, we typically just omit the 1, which is a common theme. Again, the charge of the ion depends on how many electrons were gained or lost. If you gain a negative charge, if you gain an electron, you gain a negative charge. So again, the number of protons for fluorine, we find fluorine. There it is. It's got a number 9, so it has 9 protons. And we just saw that it gained 1 electron, so we've got 10 electrons. 9 minus 10, protons minus electrons, gives us an overall 1 negative charge. So F minus. So that's what happens if we change the number of electrons. Another of our subatomic particles is neutrons. We can change the number of neutrons in an atom. So all atoms of a given element have the same number of protons, but the number of neutrons can vary. This is in contrast with Dalton's original theory that all atoms of the same element have the same mass. That's not true. Dalton was wrong. So what we get when we change the number of neutrons is isotopes. And every element is going to have its own unique percent natural abundance of isotopes. So if you go out into the world and you find a sample of carbon, or if you find a sample of copper or cobalt, and you collect a bunch of it up, and you go to the lab and you use some fancy instrumentation and you analyze that sample, you'll find a certain abundance of each of the different isotopes. Some parts of the world will have different abundances. The periodic table that we have, the number in the bottom here, that's the weighted average of all the different naturally occurring isotopes. So some samples, it might be a little lower, it might be a little bit higher, but just generally that's the natural abundance. So for example, hydrogen has 3 different isotopes that naturally occur. We've got protium, which is just the proton, deuterium, which has 2 particles in the nucleus. So we've got a proton and a neutron. We also have tritium that has 2 neutrons and a proton. You would not be able to just guess what the natural abundance of these are. You'd have to be given a natural abundance. You also don't have to know these names, protium, deuterium, tritium, but you might see them occasionally, like once in your life maybe. And we typically symbolize our isotopes in this way. So we'll have the symbol in regular text, and then kind of subscripted and in front, we've got our atomic number. Our atomic number is the number of protons. We also have superscripted and in front, the mass number. The mass number is the number of massive particles. So that's the number of protons plus the number of neutrons. And we'll see that on the next slide. So some symbols for neon, for example, 20 over 10, neon, 21 over 10, still neon, 22 over 10, also still neon. So again, for our isotope symbols, that mass number, the number of massive particles, this has the symbol A. Any guesses on what A stands for? That's true. Does anyone know where we get the letter A from, why we chose A? I didn't think so. It's, from what I found online, from German. And apologies to any Germans who may be listening in. I think it's pronounced Atomgewichte, which looks kind of like atomic weight, and I think that's basically just what it means. So that's why we have the letter A as our symbol. So A is just the number of massive particles, which are protons and neutrons. Our electrons in comparison are teeny tiny. They're a 2,000th of the size. And we can calculate the number of neutrons by looking at the difference between A, which is protons plus neutrons, and Z, which I don't know if we've talked about before, but that comes from the German word Zahl, which is number. Just what order did they show up in the periodic table, and that's the number of protons. So if we do number of protons plus neutrons minus the number of protons, unsurprisingly, we get the number of neutrons. So that'd be a calculation that you could do. On a symbol, so for example, this one that we saw for neon earlier, you do the top number minus the bottom number, and that gives you the number of neutrons. Conveniently, it's also always, except for hydrogen, protium, it's always big number or little number. In the case of protium, they're just the same. So A goes on top, Z goes on the bottom. A is always bigger than Z unless you're protium. Another way that we can write out the notation is using the symbol or the name and then following it with a hyphen or a dash. I don't know which it is, but it's one of those. So like H1 or C12, hydrogen 1, carbon 12. Now, we know that if we've got our other symbol notation, we've got two numbers in front. How do we know which number we're putting after it? Because you could 50-50 that if you weren't thinking about it. Well, the way that we know what number goes after it is if we look at our symbols, right, 20/10 neon, this 10 is the number of protons. The number of protons determines the element. So 10 and neon, these are linked. If we change the 10, it's also no longer neon. If we change the neon, it's also no longer a number 10. So the only number that provides us with different information is the top number, which would be 20 in this case, which is the mass number. So we're always going to put that number after. It's the A after the dash, or the hyphen, whatever it is. Questions about ions or isotopes so far? Confusions? It's just more rules for this very complicated game that we're playing. Okay, let's try doing some of those things. What are the atomic number, mass number, and symbols for the bromine isotope with 46 neutrons? What's some information that we're given?
46 neutrons.
We're given that we've got 46 neutrons. What else are we given? It's bromine. Bromine has what symbol? Br. What's some other information that we can get from knowing that it's bromine? We can find the atomic number. So if we find bromine, right, we see in the top right corner that 35, that's the number of protons that we have. So bromine has 35 protons, always has 35 protons. What can we do with this 46 neutrons? We can add it to get the mass number. The mass number is the number of protons plus the number of neutrons. So our number is what? 81. So our mass number, A, is 81. So we can write out a symbol. We're going to start with Br, our symbol. And then we've got two number slots that go in front. Which one goes on top? It's the bigger one. It's the 81. So we're going to put the 81 on top, and we're going to put the 35 below. There's two other ways that we can write this out. BR line, and then which number? 81 or 35? 81. Or we could write it with the full name, bromine line 81. Again, the reason that we're writing the 81 is because we can figure out the 35 by looking at our periodic table. We find the 35 in the top right corner. All right, working the other direction. How many protons and how many neutrons are in the potassium isotope given here? We have 19 protons. The protons is the easy one. And then to figure out the number of neutrons, remember that this top number is protons plus neutrons. It's our mass number. The bottom number is the number of protons. So if we just subtract these two, we get 21 neutrons. All right, let's do some ion practice as well. So determine the charge for each of these ions. We've got a cobalt ion with 25 electrons. What's some information that we're given? We've got cobalt and we've got 25 electrons. If cobalt exists normally as a neutral ion, neutral atom, how many electrons is it going to have? It's going to have 27. So we find CO for cobalt, and it's got that 27 number in the top right. The 27 is Z, which is the number of protons. So cobalt has 27 protons. It would normally have 27 neutrons as well, electrons as well. This one, the variety that we're looking at, has 25 electrons. So one way that you can figure out what the charge is look at the number of protons, look at the number of the electrons. Which one do we have more of? We've got more protons. How many more protons? Two more protons. Protons are positively charged, so it's a 2 plus. So CO2 plus. We could also do, if you wanted to just run the formula every time, the number of protons minus the number of electrons. So charge is protons minus electrons. We have 27 minus 25, which comes out to 2. It's a positive number, so we put a plus after it. So that'd be another way that we could come up with cobalt 2 plus. Okay, now try the iodine ion with 54 electrons and the nitrogen ion with 10 electrons. All right, iodine ion with 54 electrons. We need to figure out how many charges, how many positive charges does iodine have? So we find iodine. Iodine on our periodic table is the symbol I. It's got an atomic number of 53, so we're going to find that it has 53 protons. It has 54 electrons, so if we subtract 54 electrons, we get an overall 1 negative. The other way we could come up with that is we've got 54 electrons, 53 protons. We've got more electrons. Electrons are negatively charged. We have 1 extra negative charge, so we've got a 1 minus charge. So this would be I minus. For nitrogen, we find nitrogen on the periodic table. Its symbol is N. It's got a number of 7 in the top right corner, which means that it has 7 protons. It's got 10 electrons, so we have more electrons. We've got 3 more electrons, so it's N 3 minus. We could also subtract our 10 electrons from our 7 protons, and we get 3 minus, or negative 3. Questions? Beautiful. We can also work the other direction. So starting from an ion, we can find the number of protons and the number of electrons. So S2 minus, S is sulfur. We can find sulfur on our periodic table. It's in the right side in our main group. It's got a number of 16 in the top right corner. What's that 16 mean? Yeah, that's the number of protons. So the Z is 16, or the atomic number is 16. So it has 16 protons. To have a negative charge, what does that mean about the number of electrons? 18. It has 2 extra electrons, 2 more electrons than the number of protons. So it has a 2 negative charge. Two more electrons than protons. So 18 electrons. We could also work that equation that we had. Charge is the number of protons minus the number of electrons. We've got charge. It's a negative 2 charge. We've got the number of protons. It's 16. Put in X for our number of electrons, and we would get that X equals 16 plus 2 when we switch the X and the negative 2, which is 18. Okay, more on the ions. So that number associated with the A above each main group column, 1 through 8, gives the number of valence electrons. Valence electrons are just outside or reactive electrons. We'll come back to this in several chapters. But this number of valence electrons is important, as we'll see. So the reason that this helps us out now is that our main group elements, so remember that's things in the first 2 columns and things in the last 6 columns. Our main group elements tend to form ions that have the same number of valence electrons as the nearest noble gas. The nearest noble gas, just like exits on an airplane or a school bus, may be behind you, or maybe behind the element. So for things like potassium, K, if we don't think about the fact that the periodic table wraps around it, would look like krypton is our nearest noble gas. However, krypton is number 19, that's right next to 18, so argon is actually our closest noble gas. So you can move back and up a row as well to get to the nearest noble gas. Is that all that I have in the slides to talk about this? That's awesome. Okay, so we'll do some examples. I'm apparently missing a slide or 2. So let's do potassium again. Potassium, K, has 19 protons. When it forms an ion, it's going to be like the nearest noble gas, which is argon, in terms of the number of electrons that it has. The lights are zapping for some reason. Okay, so it's going to be like argon, which is the nearest noble gas. for the number of electrons. How many electrons does argon have normally?
18.
Normally has 18. So if we've got 19 protons, 18 electrons, what's our charge going to be? One positive. So we've got one extra proton. So potassium is going to be K plus, for example. The other side of the periodic table, let's look at selenium. Selenium has the number 34. So it has 34 protons. It wants to be like the nearest noble gas. The nearest noble gas is krypton. We just move 2 spaces over to the right. So ion like krypton in terms of its number of electrons, which is 36. So selenium, when it forms an ion, is going to have 36 electrons and only 34 protons. The number of protons doesn't change because that would change the element. So if it has 36 electrons and 34 protons, its charge is going to be 2 negative because it's got 2 extra electrons. So 2 more electrons than protons. And I think this probably comes up in many slides from now, but just to bring it home and put this information here for us. Okay, moving on to chemical formulas. So we can combine different elements. For example, you can combine sodium metal and chlorine gas. Maybe we can just turn those lights off. Pause real quick. All right, so sodium metal and chlorine gas can react with each other. And many other chemicals can also form from different elements. And so we need to be able to represent all of these different chemicals. There's more than you care to know about. And we do that with a chemical formula. So our chemical formula is going to indicate the elements present as their symbols and the relative number of atoms of each as subscripts. By convention, a subscript of 1 is omitted. This kind of just helps keep things looking nice. It also saves us writing a lot of 1s occasionally. So for example, for this chemical, CH4, we've got carbon. We don't have a subscript, so we just have 1 carbon. We also have hydrogen present. We've got a subscript of 4, meaning that there's 4 hydrogens. So the hydrogens stay together. All right, we've got 4 of them. We've got just 1 carbon. In one of these molecules, or one of these combined chemical units. 1 carbon, 4 hydrogens. And this is sort of like a name or a designation for the chemical. So CH4 is a unique chemical, and it's different from if we change any of the letters or numbers. They're all different chemicals. And we'll learn the very fun and very robust naming convention system in about 18 slides from now. We'll learn parts of it. We can also have chemical formulas, groups that act as a unit. These are called polyatomic ions. Poly for many. So many atom groups. And they're ions if they have a charge. There are some polyatomic ions that we'll get the chance to memorize for the class. And you'll find those in that sheet I mentioned at the start of class. If you have 2 or more of a polyatomic group present, then we'll place them in parentheses and a subscript goes outside of that. So for example, PO4 is a phosphate group. And in this chemical, we've got 2 phosphates. And in order to show that we've got 2 phosphates, 2 of that whole PO4 group, we put parentheses on the outside. And then this 2 indicating that we've got 2 of whatever's inside the group. This is helpful for a number of reasons. We can recognize that PO4 is a group. This is something that we'll probably be able to do by the end of the class. And so writing the 2 outside, we know, okay, well, there's PO4 groups. If you write this as Ca3P2O8, you probably won't recognize what P2O8 is. Your brain isn't going to easily or immediately put together, okay, P2O8, that must be 2 PO4s. So that's why we do the parentheses, to let us know that it's actually 2 PO4 groups. When we do these parentheses on the outside, if we were to count up how many of each of the atoms that we've got, we can see that we've got calcium by itself in the front. It's got a subscript of 3. So we have 3 calcium atoms in one of these whole formulas. For our phosphates, our phosphate inside, or our phosphorus rather, inside, has an invisible subscript of 1, but we've got a 2 outside the parentheses, and so we do 2 times the 1. That's what we're doing here. 2 phosphorus atoms. To figure out the number of oxygens, we've got a subscript of 4 inside the parentheses, plus the 2 outside, 2 times 4, we get 8 total oxygen atoms. So the 2 that's on the outside multiplies both the numbers, or all the numbers that are on the inside. So we can figure out how many of each of the atoms we have. As I mentioned earlier, the subscripts are part of the compound's definition. It specifies a particular compound. So for example, CO is the chemical formula for carbon monoxide, which is very bad to breathe. It's toxic to you. It limits your body's ability to uptake oxygen. So you can end up with carbon monoxide poisoning and some other fun symptoms that come along with that. Whereas CO2, which just has 1 extra oxygen, CO2 is carbon dioxide, and we're putting that out right now. Our bodies just produce that normally and naturally. It's also bad for you to breathe in too much of it, but not nearly as bad as CO. So if we want to represent compounds, we do that with chemical formulas. We've got several types of chemical formulas. We've got a molecular formula. Our molecular formula gives us the actual number of each atom. Or element. So this is the actual number of pieces that go into making up that molecule or that unit. So for example, glucose has the formula C6H12O6, meaning we've got 6 carbons, 12 hydrogens, and 6 oxygens. That's the actual number. If you were to zoom in with a microscope and look at the glucose molecule, that's the number of each of those elements that you would see in one unit. There's another formula that's related that gives the relative number of atoms. So the empirical formula gives us the relative number of atoms, or simplified number of atoms. And empirical, another way that you can think of that is just experimental. So if you were to take this compound and hit it with a little hammer and break it into all of its component elements, you wouldn't know how many went into each unit. So you wouldn't know that there were 6 carbons, 12 hydrogens, 6 oxygens in each individual unit because you've broken it up into tiny little pieces. This is like if you took a Lego set and you tore it apart into all its different pieces and you counted up all the different number of pieces. Okay, how many of each do I have? You can figure that out. And what's your ratio? You could figure that out, but you wouldn't know how many went into each of the little Lego men that you had necessarily. So our empirical formula, again, this is a relative or simplified ratio of our atoms. So for glucose, we can divide each of these subscripts by 6, and that would give us an empirical formula of CH2O. The empirical and molecular formula can be the same. So if it's already simplified in the molecular formula, then the empirical formula is the same thing. We'll do a lab, I think, where we come up with an empirical formula for a compound. So we'll get to see how we can just come up with that ratio. Questions about formulas? Okay, we also have different types of elements. So a lot of our elements exist as atoms, one singular smallest piece just by itself. Most elements exist as single atoms. However, there are also some molecular elements. These exist, the ones that we learn, exist as diatomic molecules. So they don't like to go alone. They normally and naturally exist as two atoms linked together. And we've got them in a list here. There's also some mnemonic devices. So Brinkelhoff is one of the mnemonic devices. So this is just all the chemical symbols put together. There's also H7. So if we look at our periodic table, hydrogen is in the top left, hydrogen, and then nitrogen, oxygen, fluorine, chlorine, bromine, iodine kind of forms a 7 shape. That's where the H7 comes in. We also have this sentence, horses need oats for clear brown eyes, where eyes is actually the letter I, not the word I. And I'm not much of a horse girly myself, so I'm not sure if this is true. I'm guessing that it's probably not. But we do know that horses like oats. I assume that they actually eat oats. So this is reasonably close to the truth. It's good enough for our purposes. This isn't a biology class. So horses need oats for clear brown eyes, Brinkelhoff, or H7. So all of those elements, naturally and normally in the world, if you go out and find them, they'll exist by themselves with 2 units bound together. So O2 and N2, the things that we are breathing in right now that make up the major components of our air, normally exist as N2 and O2. That's not to say that you can't have them by themselves, but that's just the way that we normally find them. We also have different types of compounds. So just like we have different types of formulas, we also have different types of compounds. We've got molecular compounds that are formed from 2 or more nonmetals. These are nonmetals only. No metals in my molecular compounds. We also have ionic compounds that contain 1 or more cations. Are cations positively or negatively charged? Cations positively charged. So we've got 1 or more cations paired with 1 or more anions, which is negatively charged, and usually, almost always, contains a metal. So if there's metal in there, I bet it's an ionic compound. One exception is ammonium. So we could also have NH4 plus as one of our cations or as our cation instead. Good flashcard material. Molecular compounds, nonmetals only. Ionic compounds, metal and a nonmetal or positively charged polyatomic ion and anions. So ionic compounds are things, again, that are generally composed of a metal and a nonmetal. They're called ionic compounds because they're made up of ions. And our basic unit, or our smallest unit, is the formula unit. The formula unit is just the smallest repeating part. And the reason that we use a formula unit instead of a molecule is that because ionic compounds exist in these 3-dimensional arrays. So it's alternating positive and negative charges as long, as deep, as tall as you can possibly imagine with ions, which presents some issues. If you wanted to count up the actual number of each of the cations and anions, it would take a long time and you would end up with absurdly large numbers in almost every case. And so we just use the smallest repeating unit to specify that compound instead, because it's going to be the same little chunk, just copy pasted sextillions of times or something like that. So another way we can think of this is that formula units are always simplified. The subscripts, at least, are simplified. And we'll see examples of that. Okay, let's think about each of these types of substances. We've got elements. We can have either atomic elements, where it's just that one element by itself, just one little atom by itself, or we can have molecular elements, where we've got two of the atoms together. They don't like to go alone. We've also got compounds. We've got molecular compounds that are nonmetals only. We've got ionic compounds that are cations positively charged and anions negatively charged. And these typically contain a metal. Okay, so looking at what we've got here, we've got Fe. What is Fe? It's an element. It's just one chemical symbol, right? So we know that it's an element. Is Fe atomic or molecular? Does it exist as one atom by itself, or is it paired up with another of itself? Atomic or molecular element? Does it have a subscript of 2? No. So it's an atomic element. It's also not part of our mnemonic Brinkelhoff, our H7, so looking at hydrogen, then nitrogen to fluorine and down. It's not one of those elements, and so it's atomic. It's also not part of our horse's knee oats for clear brown eyes mnemonic device. And then PCl3. Do we have an element or a compound? It's a compound. We know it's a compound because we've got multiple element symbols. Then we have to think about what kind of elements do we have. Let's find them on the periodic table. We've got phosphorus, P. We've got chlorine, Cl. Those are both in the upper right part of the periodic table. So those are both nonmetals. So we've only got nonmetals. Does that make it molecular or ionic? Molecular. Yeah, it makes it molecular. Because it's only nonmetals. And then LiBr, we've got another compound. We've got more than one element symbol. Is it molecular or ionic? Let's find out what kind of element each of these is. So we've got lithium. Lithium is one of our alkali metals. So it's a metal. We've got Br, which is one of our halogens, bromine, which is a nonmetal. Since we've got a mix of metal and nonmetal, this is an ionic compound. Metal and nonmetal. And then last but not least, we have the thing that we survive on, oxygen gas. Is oxygen gas an element or a compound? Oxygen is an element. Does it normally exist as just O, or is it O2? It's O2. It is a molecular element. We know that it's molecular because it shows up in our Brinkelhoff. It also shows up in the 7 shape of our H7. It's also the oats of horse's knee oats for clear brown eyes. So this is O2. Questions about any of those? All right, ions. We can have monoatomic or polyatomic ions. We've got a lot of ions with predictable charges. So for ions with predictable charges, if you look at the ions list that you need to memorize, this is, I think, half or more of the ions that you need to have memorized. They have predictable charges, and we can figure it out based on our periodic table. So we've got our metals in our group 1A, which form 1 plus charge, 2A, which forms a plus 2 charge, and 3A, which forms a plus 3 charge. So if we look at our periodic table, our first column, our alkali metals, those are all going to form a 1 plus charge. If we look at our alkaline earth metals, which is 1 over, it's also 2A, those are all going to form a 2 plus charge. If we skip our transition metal elements and look at aluminum and gallium, which are metals, in 3A, those are going to form 3 plus charges. So that knocks out a ton of our ions to memorize. It's just 1, 2, 3. We've also got zinc and silver. I think cadmium also shows up sometimes. So I'll add that in. Big C, C, D, 2 plus. So zinc, silver, and cadmium, Zn, Ag, and Cd, these are all transition elements, transition metals. The way that we can remember them is we would have to remember, the way that I like to remember them, if we remember that aluminum is a 3 plus charge, it's in the 3A. Aluminum is a 3 plus charge. If we look at aluminum, zinc, and silver like a little staircase, aluminums are 3 plus. If you step down 1 stair, you're at zinc. You lost 1, you step down 1, so it's a 2 plus, and that's what the charge is. You step down 1 more to silver, silver plus. And cadmium is also under zinc, so it's a 2 plus. So a little staircase. We've got Al, this is our 3 plus. We've got Zn, which is our 2 plus. I think I have this written down on a slide somewhere too. Cd is also a 2 plus, and then we've got silver, which is just a plus. So we got a little staircase. And then for our nonmetals, the charge is the group number minus 8, the A designation group number. So if we look at our halogens, these are group 7A. So 7 minus 8. One negative. If you step over one more to the group that's under oxygen, these also have a name. It's chalcogens, which starts with a C. So chalcogens, these are group 6. And so these are all going to be 2 negative charges. We step over one more space to things that are under nitrogen. Those also have a name, pnictogens, which of course starts with a P. So pnictogens, or things under nitrogen, those are going to be 3 minus. So one way that you can remember that is do the group number with the A designation minus 8. That'll give you your charge. Or if you look at the number of spaces you have to move over to be in the noble gas column. So chlorine, how many spots do we need to move over to get to argon? 1 spot, 1 negative charge. Sulfur, how does to move over how many spots to get to argon? 2 spots, 2 negative charge. Phosphorus, move over how many spots to get to argon? 3 spots, 3 negative charge. The other reason that this works, we saw this previously, they like to form ions that are like their nearest noble gas in terms of their electrons. So phosphorus normally has 15 electrons. It has 15 protons. When it forms an ion, it'll have 18 electrons, which is 3 extra electrons, 3 negative charge. And here it is on a slide. I'll add in cadmium and gallium. So our little 3, 2, 1 staircase. So this knocks out a ton of things, and so you can just memorize for these different columns. For A, these tend to not form ions, at least for the top couple. So carbon, silicon, germanium tend to not form ions. And I guess we'll stop there. I am going to do some extra lecture in lab for people today. I don't know if I'll repeat that lecture on Wednesday. You might just have to watch it as a video.